Okay, so we want to look at linear transformations. And with linear transformations, there are just three themes or three sections that we have to cover. So one involves just the definition of a linear transform, and the other one involves the definition of what we call a kernel and the range of a linear transformation. Then the last part, it deals with finding a matrix equivalent of a linear transform. So this is what we're going to try and talk about in this section. So let's begin. So the first thing that we want is the definition of a linear transformation, what it is. So a linear transformation, T, is a map which takes us from one vector space V to another vector space W, like that. So when we discuss a linear transformation, you should know that transformations, they are objects or they are operators which allow us to move from one vector space to another. So there's some sort of a bridge. That's why some books, they actually use a notation like this, that a transformation T, which is such that it takes us from one vector space V to another vector space W, like that, satisfying the following properties. You see, so what we refer to as a linear transformation must satisfy the following properties. So a linear transformation must be such that if you give it as the zero of the first or the zero of the vector space V, it must produce for you the zero of the vector space W. You see, so that's one of the first conditions that must be met if a transformation is linear, because there are many ways of constructing or of coming up with a construction that allows us to move from one vector space into another vector space. But if we want one which is linear, then these properties that we're stating here must hold true. So the first one is that T of these must produce that. Then the second one is that if you take a scalar multiple of T1 V1, where V1 is an element of V, like that, then you must get alpha 1 T V1 plus alpha 2 T V2, like that, with V1, V2 elements in V. So these are actually everything that needs to hold true when we are discussing what we call a linear transformation. So any transformation which satisfies these two properties is said to be linear. So once these are verified, that's true. But you might find that in some cases, this property number 2, it is split into two equivalent properties that can be verified separately. So this one property can be split into just verifying that T of R lambda V is equal to lambda T V, sorry, then 2 T of V1 plus V2 is equal to T of V1 plus T of V2. So if you can verify these two separately, they're equivalent to property 2 as well. So if you are given a linear transformation which satisfies these, then this is what we refer to as a linear transformation. So typical problems in exams are like you can be given a description of a transformation which we do not know whether it's linear or not. Then you can be asked to determine if this given transformation is a linear one or it's not a linear at all. So are you familiar or are you okay with answering such types of problems?
Sorry, can you repeat your question?
Yeah, I'm saying like a typical questions concerning this definition in exams, it's whereby you are given a description of a transformation, which for as yet, we do not know whether it's a linear transformation or it's a non-linear transformation. So my question was, are you fine with solving these type of problems where you are asked to verify if a transformation is linear or is not linear?
I think I'm fine with it because basically what we have to do in those types of questions is we see our two conditions, I and 2, and we basically have to do both of our transformations in that way. And then if they equal the same thing, we know it's a linear transformation. If not, then it's not a linear transformation. Am I right?
That's how it works.
Sorry?
So, yeah, that's how it works. So if you're fine with those questions, then we can move on to the next thing. So the next thing that we want to discuss is two things that are quite important on this subject, the kernel and range of a linear transformation. So the kernel and the range of a linear transformation, that's what we want to discuss right now. So what is a kernel and what is a range? You see, so the kernel of a transformation T which takes us from V to W, is the set. So it is the set which is described as follows. It is the set which is such that it consists of elements V such that T of V is equal to the 0 of W. Like that, you see. So this kind of set which is found in this way is what we refer to as the kernel of a linear transformation. And it is denoted by Kel T like that, you see. So this is what you have to know to understand clearly what this definition is trying to teach us. So what exactly is a kernel? So a kernel is something like this. So if you go to vector V, remember the vector space V is made up of objects which we denote by V arrow because we pretend they are vectors, though they are not necessarily vectors as we know vectors from areas like physics and the likes. So they are just objects, but we call them vectors. So if you can find all elements in big V, which are such that every time when you provide them as arguments to a given transformation T, you get a 0 vector of W. Then we refer to all such a collection as the kernel of the linear transformation. So that's what the kernel is. All elements which are mapped to the 0 element of the other vector space are what we refer to as the kernel of that vector space. So that's it. Then what about the range? The range, on the other end, is the set. So the range on the other end is the set which consists of elements W such that they exist V element of big V with T of V equal to W, like that, you see. So we have what we call the range of a linear transformation, which is just the collection of all end products of you taking V and putting V into T as an argument. So when you transform the vector space V, a collection of sets or vectors that you get out of that make up what we call the range. So the range, I think it follows nicely from its definition of functions. How we understand it in function, it is the same thing that happens also in this case. You see. So the range is denoted as ren T and is defined by that. So it just refers to all W such that TV is equals to W, like that. So are we cool with these two definitions, by the way?
Yeah, good.
Okay, cool. So if you are aware of all this, then we are close now to approaching the problem that you want us to solve. But there are some theorems that are quite important or worth knowing when it comes to this section, and think they can be very helpful in answering the question that we have already asked. You see. So what does the first theorem say? So the first theorem goes as follows. It says that a linear transformation T from vector space V to vector space W is said to be one-to-one if and only if the kernel of the linear transform is just the zero vector of W, like that. You see. So this theorem is quite important as it is going to be used in answering one of the questions that you have already asked. So one thing that you should know is that linear transformations, they play the role of functions in vector spaces. Remember, functions are functions in sets. They are mappings that allow us to move between two sets. But now when we replace those sets with vector spaces, where vector spaces are still sets, but we have introduced some operation of addition and scalar multiplication inside, which distinguishes them from that. Then if we want to bring in the notion of function in vector spaces, we bring that in the form of linear transformations. You see, so transformations are simple functions of vector spaces. So which means we still have the same classification scheme that we used for other functions. Remember, we had different types of functions when we were discussing functions in different areas, where we were taught about injective functions, surjective functions, and bijective. So do you still recall all those definitions?
Bijective is both injective and surjective. I just want to go over that because surjective is like, can we go over practical examples? Like, will surjective mean that it can have, for every X value, it can map to more than one Y value? Or yeah, can we just go over those definitions again, please?
So first, yeah, we have gone to one-to-one. So one-to-one is the same meaning as saying injective. So a function being one-to-one is just the same as saying injective function. But now the definition is quite different here because we are not stating it in the same way we will do when we're talking about sets with just functions. So here being one-to-one simply means the kernel only has one element, which is the zero element of W. But what about a surjective function now? You see? A linear transformation
Sorry, just a quick question. And one-to-one means that for every X value, it only maps to one Y value.
Yes.
And vice versa. For every Y value, it only maps to, for every Y value in the codomain, it only maps to one X value in the domain, sorry.
So like let's try to illustrate with the diagram. So suppose this is our V and this is our W. So it means to each object in V, there should be one arrow going to W.
Yes.
For each object, we should just have one arrow going to W, not two arrows coming out from there, or maybe two arrows going to two different things, but we should just have only one arrow going to an element in W. So also if there's another object, we still have to have one arrow. So we do not care what happens this side. These arrows, they can meet in W at one point, but here when I look at one point, they should be just one arrow coming out of that point. That's what we mean by one-to-one.
Thank you. That was helpful. Yeah.
So now a linear transformation T from V to W is said to be surjective if for each W, an element of big W, we have that, or they exist V, an element of big V, such that T of V is equal to W, like that. So this is what we mean now when we say a linear transformation is surjective. So what does it mean? So same illustration again. Suppose I have my two vector spaces V and W. Now my focus is here, not here. So suppose I look at each element that is in W. If I can see an arrow that is associated to each and every element in W, then W is called a surjection. You see, so I should see an arrow that each element in W must be linked with an arrow. But if there are elements in W whereby they do not exist arrows in them, we say that this is not a surjection anymore. So a linear map is said to be a surjection if for each element there is an arrow, which shows that there is some element in this set where the arrow is coming from, mapping into that element. So that's what a surjection is all about.
Can we think of any practical examples in terms of a graph where a surjective function would look like?
So let's try to think of something. Okay, suppose I have a graph like this one. This is my graph. There is an asymptote here at this point.
Mm-hmm.
Let me first check if I'm doing it the right direction. No, I'm doing it the right. Am I doing it the right direction? I think I'm supposed to draw it in a vertical way. I think this has to be vertical. So let's try to do it this way. I'm trying to see if I can create something that can explain what we want here. Does this make sense? Because we want to create a situation where if I were to draw a horizontal line, something like that, then these horizontal lines must not correspond or must not meet this graph at any way like this. Because if I were to draw a horizontal line, this line will meet the graph here, and this graph line will meet this graph there. So we'll have two x values which correspond to that y, but this is not what we want. Because what we want at the end of the day is that we must have a horizontal line whose y value, whose y is an element of W, but when we continue it to the graph and bring down, there must not exist any x values that correspond. So there must not exist any point of intersection between this horizontal and this graph. And right now, I'm failing to think of one graphical example that we can use. It's always simple to use these types of plots most of the time to illustrate such ideas. You see?
Okay.
Because that's the only best way to illustrate, because once you understand that, remember, the vector space W can have many different elements in it. And here also we can have as many different elements as possible in it. But what we require all the times is that in set V, all elements in V, it's like a must be that they should always be associated with a single arrow coming out. Do you see that? So the only thing that we care about is providing each element in V an arrow which takes it to the other side. But it is not always the case that each element in W is associated with an arrow. But if we have defined our linear map in such a way that elements that are here also, all of them, they are associated with arrows, then we say the map is surjective.
Okay.
Is that clear, or are you still?
Yeah, I think it makes sense. As long as there's every point in our codomain has a point which maps it in the domain, then it's a surjective, right?
Yes.
Okay.
You see. So that's what we need. We need to have an arrow in each and every element in the codomain.
Mm-hmm. And then the injective function would be, it's where we look at V and we say for every point in V, there's a point in W.
Yes.
Okay,
so,
at least maps all.
Yeah, so there should be arrows coming out of each and every point. So if each and every point is associated with an arrow, then this is an injective function.
Okay.
You see, like that. Once you miss, once there is exists an element in V in which there is no arrow associated with that element, this is not a map at all. A map must check everything, all of V, and take it to something in W.
Okay.
You see, so I can take everything in this set and take it to only one element of W. So if I leave out all these other elements without any mappings coming from this side, then this does not, this is no longer a surjection at all. But if there are arrows in each and every point, then it becomes a surjection.
Okay.
Okay, cool. So if we're now clear with the definition, I think it's time now to look at problems. I don't know if there are any other theorems that I forgot, but I think, yeah. Oh, okay, yeah. There's this theorem, which I think also it can be quite useful. So let me state it again. So theorem number 2. You see, suppose T is a linear transformation such that T maps V onto W. See? So if V has a basis, if V has a basis, what do we call this thing? If V has a basis, PV, then T of PV spans range of T. You see, so this theorem, I think, also is going to be important in the problem that you also gave to me. So let's understand what it says, because it's a very important theorem. So I think now you are fine with what we mean by basis. Are we clear? Are you fine with the definition of a basis as far as linear algebra is concerned?
Mm-hmm.
So remember what we refer to as a basis. What we refer to as a basis, EV is just a set of vectors which I can refer to as S1, S2, S3, ... to Sk, which are such that every other element in V can be written as a linear combination of these. That's how we understand what a basis is. If you take linear combinations of the basis elements, they produce each and every element in that vector space. You see, but a basis is a vector in its own right. You see, so if you check, so if you now find T of Si, we know that if you were to find T of Si, obviously you will get alpha I as another vector. Do we agree on that? If you take Si, where Si means any one of these, you will get alpha I as a vector. And do we agree that alpha I will be an element of W?
Yeah.
You see? So that's what we know so far. So when we take that alpha I, it will become that. So suppose now you collect all these alpha I. You see? Suppose you collect all these alpha I. So what this theorem is trying to tell us is that if you take a mapping of all the basis elements, they will produce for you new elements which are going to form another basis for your set or for your vector space W. But it's not actually a basis because it won't be satisfying all the properties that we need for something to be a basis. But one good thing about all these element alpha I is that if W is an element of W, then W can be written as a sum of some constant K1 times alpha I, like that. So that's what this theorem is trying to teach us, that if you know the basis of V, it is easy to find should I call it a basis? It's not actually a basis, but if we know a basis for V, it's actually easy to get vectors that whose linear combinations can produce the whole of the set W. You see? So if we can get something like that, because remember, what are the two properties that must be satisfied by a basis?
It's independent.
Yes, they should be linear independent.
It's a linearly independent it's linearly independent where we can write our basis as alpha not alpha, sorry, lambda S1 plus lambda S2 is equal to 0, where all of our lambdas are equal to 0, which tells, because our vectors can't equal 0.
Yes.
So, yeah.
So that's perfect. That's what I needed. So that we can actually understand what's happening here. So we need two properties to hold true for something to be called a basis. One, it must have that ability to reproduce the whole set as a whole. But the thing is, these vectors, they must be linearly independent. So one thing that I have to tell you right now is that when you take out all these vectors Si, and you plug it into your linear transformation Si, the alpha I which come out, they are guaranteed to produce the whole of the elements that are in W. But what is not guaranteed is that each and every one of them is linearly independent of each other. That's one thing that is not guaranteed by this operation.
And that's for the range of okay, using a basis. But if it was a span, just a quick question, a span is the set of all linearly
All linearly combinations.
Okay, so this is a basis, but it doesn't necessarily mean that it spans our range.
Yeah, it's our range. It doesn't necessarily mean that. It means what it simply means is that a portion of these alpha I elements is actually the basis that we need. You see that? A portion of them. So it's not the whole of alpha I's, but just a small portion of them. So now we have to, let's say we have 5 of these alphas, and the vector space that we are dealing with, we know that it can be created by 3. It means there must be 2 which are dependent on the other. So we have to figure them out and take it out of the box, such that we remain with the most fundamental ones, which can recreate everything.
Okay.
You get that?
Yeah.
So yeah, that's the theorem that we needed lastly for handling the problems that you have. But before we move on to that section, I think now it's time to look at the first questions in your problem. So let's look into it now.
Sorry, was it the one that I sent you?
Yes.
Okay, hold on, let me just pull it out. 2 seconds. Okay, sorry, I just want to split my screen. There we go. Good to go.
I don't know why it's, you want to copy and paste it where we are working, but it's coming out in a way that, so okay, so this is the problem. This is the problem. So let's get to it. So it says we have a linear transformation which takes us from R3 to 2 by 2 matrices. And we are told that it's a linear transformation already. So they say let B and C be the basis of this and that. Find a basis for the kernel of T. So they say find a basis for the kernel of T. How do you answer such a problem like this one? So solution. So part A. So how can you answer part A? So first we have to ask ourselves, what is the kernel of T? Remember. So remember the kernel of T, it is all elements V such that when you say T of V, you get the 0 of W, if you still remember the definition. Yeah. Like that. Now, for this problem that we are dealing with now, what is the 0 of W? Do you agree that the 0 of W is just the 0, 2 by 2 matrix?
Yeah, that's true.
So for this, what we're dealing with, the 0 is just this element. So now we want to find V's such that all these V's are mapped into this. So now remember, this has to be generalized. So what I'm going to do, I'll say, let this V that you are talking about be alpha 1, alpha 2, alpha 3. You see?
Yeah.
So if T of V is equals to the 0 of W, then what? Then what? So if T of V is equal to 0 of W, then what? So we come. So first we have to now use the definition to know what T of V is. So what is T of V? According to the definition, if you put V, it outputs that. So I'll get alpha 1 plus 2 alpha 3. So I'll get alpha 1 plus 2 alpha 3. And then I'll get minus alpha 1. Then I'll get alpha 1. Then alpha what there? Alpha
So can
1.
you please repeat? I just want to see what you did. So that's what our transformation is equal to. Okay, cool. I got that.
Sorry, I put the wrong subscripts there. So here I'll have this, and then I'll have here, then I'll have alpha 1 plus 2, alpha 3. So I know that this has to produce that. You see? So this is what is happening just because we're using the definition of what a kernel means. It means we're looking for all V's, which when we input them in the transformation, they produce the 0 vector. So it means what we have to simply do now is to solve these equations. So now, what do we see here? Do we see that we have two matrices, one on the left and one on the right, and they are said to be equal? So what is it that follows when two matrices are equal?
Well, we can basically write them as equations.
Yes, the element must be equal also position wise.
Yeah.
So it means alpha 1 plus 2, alpha 3 must equal to 0, and alpha 2 must equal to 0. You see that? So this implies alpha 1 must equal negative 2 alpha 3. So what is V? So what is V? So do we agree now V is equals to what? Remember, V is equals to alpha 1, but alpha 1 is negative 2 alpha 3. Alpha 2 is 0, and alpha 3 is 3. So this becomes alpha 3, negative 2, 0, 1. So this means this is the basis that you are looking for, because we see that every vector V that we need is going to be a multiple of alpha 3.
Yeah.
So that's it. So that's what we're looking for, because the question was saying, find a basis for the kernel of T. So that's the basis that we're looking for. It is this element. See, so therefore, basis is, you might have gotten a different one if you took things differently. Maybe you chose to say alpha 3 maybe was the subject and you wrote everything in terms of alpha 1, you are going to get a slightly different thing, but the basis is just the basis. They don't have to look alike, they must be scale elements of one another. So did you get this problem? How it was solved?
I understand this.
Okay, cool. Now they say find the range of T and a basis for T for it. So find the range of T. So do you see that this one actually is a very simple one? What do you think? How are we going to answer this one? I think by now you must have an idea.
What did the question say? What is the range?
Yes, it says what is the range of T and a basis for it. So we want the range of T and its basis.
Well, I think we can find a range for it, but by basically just finding its basis.
You see that first, we just have to evaluate this.
Ah, the range of the basis for the y of the kernel, though.
But why am I using this? Let's go back to, remember this. If this is a linear transformation and you know the basis BV for V.
Yes.
You see? Okay, I see. So what we need the basis of V. Then we can now get the range of that. So not that. Yeah, let's not use that of the kernel. So exactly. So I was now using something out of definition. So we need the basis for R3.
Yes.
To use our theorem. Now, so what is the basis for R3?
It's just the matrices of 1, 1, 1, 0, yeah. That one, yeah.
So that's the basis for R3. So what we're going to do now, we are going to check these and plug each of these into the transformation. So we'll find T of 1, 0, 0. What is that going to be? So let's go to the definition.
Yeah.
So do you see that x2 and x3, they are both 0? So if x2 and x3 are both 0, it means these will vanish and these will be 0. So we'll be left with only the position for the x1 and the x1. So we'll only remain with 1 here and 1 there, everywhere 0. So we'll get 1, 1, then everywhere else 0. Then same thing, we go to T of 0, 1, 0. So you see x1 is 0, x3 is 0. So now let's take and see. So if x1 and x3 are both 0, you see that these elements will become 0, while here we'll have 1, negative 1. So this will be 1, negative 1. 0. Then also we find T of 0, 0, 1. What is that? So x1 and x2 both is 0. So what is going to happen? x1, so x2 will be zeros and x1 and x2 will be zeros, but x3 will be 1. So we have 2, 2 this side. So we'll have 2 here, 0, 0, 2 there. Now, what do you see?
Oh, it's this base, that firstly, that's a multiple of the identity matrix, number 1.
Yes, but do you see that this one is actually dependent on this one?
Yeah.
So do you see that we have to scratch off this one? Then if we scratch off this one, these two will be linearly independent, meaning they will form the basis that we're looking for.
Yes, that makes sense.
So therefore, basis of range T is equals to what? 1, 0.
Wouldn't our range equal that? But then our bases would be the input, the 1, 0, 0 and the 0, 1, 0.
I'm writing them in a form that is supposed to separate them. So this is our basis for the range of T. But is this the range? This is not the range. What is the range? The range of T is just scalar multiples of these. So it's alpha 1, 0, 0, 1 plus beta 0, 1 minus 1, 0. That's the range.
Yeah.
Do you see that?
Yeah.
So the top is the basis, then the second is the range, meaning for whatever arbitrary value of alpha and beta that you choose, you can produce every element in W. So that's the range. So is that clear?
It's clear.
So now they are saying which of the following statements are correct? I, T is injective, but not surjective. You see. So first, let's ask, is T injective?
Which of the following statements? I would say T is injective.
Yes. So we see that T is injective. That's one thing that we see for sure. But is T surjective?
I would say we don't know, so no, we don't know.
It's actually not. But
Yeah.
because why do I say so?
I would say the reason I said it maybe might not be subjective is because we don't know if every element, it's not, okay. We don't know if every element in our range W will map back to that matrix that we have there of x1, x2 plus 2, x3.
Yes.
Yeah.
That's it. So let's show you something. Do you see that for an element in M2 to be mapped back, it must be rewritable in this form?
Yeah.
You see, it must be rewritable in this form. So the question is, are all 2 by 2 matrices writable in this form? It's not possible. You can put a counterexample and say 3, 3, then 5, 7. This cannot be. So
in that form.
It cannot be mapped to something because it cannot be written like that.
Exactly. Yeah, that's true.
So
it's injective.
It's injective, but not surjective.
That makes sense, yeah.
So I think we're clear about that one. Then part D. So are you also challenged by these type of questions, part D?
Yeah.
Okay. So we are going to explain how to tackle problems as part D, but I'm not going to do or write stuff in more rigorous stuff. I'll just make it simple so that it becomes very much easier for you to do after just explaining how you go about the process. So I'm not going to work it out. You are going to work it out on your own because it's going to be very simple afterwards.
Okay.
So how do we convert? So we want to talk about the matrix of a linear transformation. Matrix of a linear transformation. So that's what we want to discuss now at the moment. So first question is, why are we interested in actually having that ability of being able to represent all linear transformation in matrix form? Why do we need that? So the motivation behind this is that if a linear transformation T of U can be written in matrix form so that it appears in this form, then all the other definition becomes so simple to find. You see, so this thing that we refer to as the kernel that you were looking for T, it becomes just the null space of A. You see, then two, the range of T that we're looking for simply becomes the column space of A. So that's why it's very important for us to know how to write each and every linear transformation in matrix form, because it provides a much simpler way of finding these two matrices, the kernel and the range. You see that?
Yeah.
So that's why it's very important. But how do we do it? How do we do it? How do we do it? So to do it, you have to have an understanding of this concept. Coordinate vector with respect to basis B maybe, like that. So are you familiar with the concept of a coordinate vector with respect to a basis?
Mm-hmm.
Are you familiar with this concept?
Yeah. Well, do you think we could just recap it, please?
What?
Do you think we can just recap it if you can run through it again, though?
Okay,
please?
okay. Let's recap it, what it means. Suppose I have a linear transformation, or suppose I have a vector space. So suppose I have a vector space which goes from V to W, and if BV is a basis of V, which has the elements, let's refer to those elements as V1, V2, V3 dot V4. Suppose BV is the basis for V, which is made up of those elements. Let me say not V4, but VK, sorry. So VK like that. So suppose BV is a basis for V, which has those elements. Suppose now I take any other vector in V. You see, suppose I take any other vector. Do we agree that if I have a basis, it means any other vector that I take in B can be written as a linear combination of these basis elements?
Yeah.
So if I have...
Hold on, so quick question. What would be the difference between a span and a basis? Because if this basis is the minimum amount.
The span does not necessarily mean linearly independent. Vectors can span something, but it's not necessarily that each of them, they are linearly independent. Some can depend on other vectors. But when we go to the extent of saying something is a basis, it means it started as a span and we strip off some things out of them that we saw we can produce them from the others. Then what we remain is what we call the basis.
Okay.
Like that. So if S is an element of V, then they exist. We know that if S is an element of V, then they exist alpha 1, alpha 2, dot, 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 alpha K, such that S can be written as alpha 1, V1 plus alpha 2, V2 plus dot, 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 plus alpha K, VK. So do we agree that if that is a basis, then any other vector S in V can be written like this way?
Yeah.
So when you collect these coefficients together and write them in coordinate form, you see, suppose you take all these and produce a coordinate like this, alpha 1, alpha 2, dot, 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 alpha K. This coordinate is what we refer to as a coordinate with respect to some basis.
Yeah.
A coordinate vector with respect to some basis. It's just these coefficients collected in that order. You see, so it should be taken as in that orderly manner in which the vectors V1, V2 were arranged in that order. So you should not just come and write alpha K here or alpha 3 here, no, but they should be taken in that order because we want to make sure that there is some uniqueness in this thing. You see. So are we clear now with what we mean by a coordinate with respect to a basis?
Yeah.
Like that. So the short way for writing this, we write it as follows. We say S BV to mean that S, it is the vector of S with respect to the basis B of V. Like that.
Okay.
Cool.
So we're basically saying that we have our basis V, which is given by BV, sorry, which is given by our vectors, and they form a basis for basically V, and then we have S, which is given as the linear combinations, where our lambdas, right? So yeah, okay, cool. And then we know that, so then we're saying S of BV is given by our alphas. Okay.
So now, if you understand this now, let's go back to the question at hand. Now, how do you answer the last question for part B, D, of finding a matrix of a transformation, or a matrix that corresponds to a given linear transformation? You see, so suppose you are given a linear transformation T, which takes us from V to W, and suppose also you know the basis of this, which is called BV, and then you know the basis of that, which can call BW. You see, so suppose you know these two bases, the basis of V and the basis of W. So what do you do if you are asked that, given a transformation, find its matrix equivalent? So what you do is, if every time you're given this question, obviously you'll be knowing all the elements that make up this set. So what you're going to do is, first step one, you will calculate T of Vi for all Vi elements of BV. Do you see? So this is what you are going to do. So you are going to calculate TVI for each element Vi in BV. Then the next step that you're going to do to solve a problem like this one is, you will then find Vi BW.
Yeah.
You see, so for each Vi that you get out of that, or let me not write it like, because it's wrong when it's written like this. So after, first you will calculate each of these. Then when you have calculated each of those, you are going to calculate TVI BW, like that.
Yeah.
You see, which means for each output that you get here, you are going to find the coordinate vector which corresponds to each output that you get here with respect to the basis of the vector space of W, of the vector space W. You see that? Which maybe I can denote. Remember, what we get here is going to be another vector, and let's denote those vectors by alpha I, which corresponds to Vi. So those vectors with respect to this basis, you will call it alpha I. So 3, so the matrix that we're looking for is then going to be found this way. So if you want to find this matrix that we're looking for, which is denoted as T, BV, BW, like this, it is found as follows. What you simply do is, for each of these coordinate vectors that we're finding here in step number 2, you are going to write them as columns. So alpha I is going to be put as a column here. Alpha 2 is going to be put as a column here, up and so on, up until you get to alpha I, putting them as columns like that. So the matrix that you're going to get is the matrix that you are looking for.
Yeah.
Are you getting that? Mm-hmm. So do you want us to do that problem, or now you can do it?
Can we run through it, please? I want to see how it turns out.
Yeah, because if you look, do you see that we are given do you see that we are given PV, which is equal to this? Then we have this, which plays the role of PW. So you will take T of all these things, and when you find them, you will get a vector obvious outside, which I will call maybe vector S1 for the first one. So what you're going to do, you're going to take S1 and find its coordinate vector with respect to PW.
Okay, I'm gonna try it.
Then you get alpha 1. So these things that you get here, you now write them in column form, because when you get them, remember, they will be in the form alpha 1, alpha 2, dot, 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 up to alpha k, like that.
Mm-hmm.
So you arrange them in columns now. So it will be alpha 1, alpha 2, dot, 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 alpha k. So for the next one, same thing like that up until you get a matrix.
Okay, I understand.
So that's how it works. So
Okay,
that's all there is to linear transformations. It's just now a matter of you practicing a lot of problems up until you are now fine with answering all the possible problems in this section.
Okay, that's great. I wanted to ask you, I don't know what your availability is.